talk about operating systems, more specifically the kernel, whose responsibility is to manage the resources available and to assign them to tasks. Operating systems are complex software projects, often filling out entire semesters at colleges and universities. Here, we just concentrate on the subjects that we need to understand for projects in embedded systems. The operating system manages the resources available in a computer system, and the chapter starts giving an overview where that operating system is located logically. Later, we will talk about the purpose of the kernel and, as an example, have a look at the Linux kernel and what it does. As we will see, the most useful part for embedded systems is the scheduler and communication among the tasks that the scheduler handles. Towards the end of the chapter, we have a look what are the existing solutions and their advantages and disadvantages. If you attended an operating system class during your studies, you know this pyramid. It shows the relationship of the programs that are executed in a computer system and the hardware and all layers in between. On top are the programs, which often depend on libraries. For instance, into our C programs, we keep including stdio.h, which provides the functions printf and scanf among others. Those libraries depend on the operating system handling the resources. Often, the term of operating system and kernel are interchangeable. Sometimes, daemons or background processes, such as the printer server, for example, are classified as part of the operating system, while access to the hardware using device drivers is a task for the kernel. In general, the kernel is very close to the hardware and knows everything that exists in the computer system and the states the resources are in. That is evident when we have a look at the main configuration screen of the current Linux kernel. At the time of this lecture, the stable version was 5.10.4. Over the years, more and more entries were added to the menu, since kernel contributions supported more devices and functionalities. Here we decide what processor or CPU the system has, or what kind of bus system will be available to shift data around. Also, the power management options, drivers for devices, including the support for the file systems such as BTRFS or ext4, can be configured. For instance, if the user decides that he does not need a particular file system, sound card or network adapter, this part can be skipped during the compilation process, resulting in a faster compilation and smaller kernel. In the end, the kernel is compiled and becomes an executable program. The difference to the program section on top of the pyramid is that the kernel provides an abstraction layer and standardized interfaces to drive the underlying hardware. Hence, not every program has to bring its own device drivers with them. So a game does not need to have support for all kinds of graphic adapters included. It just needs to know how to access the so-called application program interfaces, or APIs in short, offered by the operating system, which then takes care of the rest, no matter what manufacturer the graphics adapter comes from. The kernel does not only take care of the hardware resources available in the computer system, it also handles the memory and virtual memory if the built-in RAM becomes too small and parts of the RAM are swapped onto the hard disk to make room for more. The kernel also takes care of the I/O through the attached periphery when processors have to communicate with each other, or determines which of the processes is allowed to access the CPU to compute something and for how long. More recently, security aspects are included as well, and on the other hand, system calls are provided since forever. Whenever you open a file or search in a file, for example, these operations are invoking system calls. Those system calls are usually hidden in libraries. What does that mean? Let's have a look at an example. Imagine an embedded system that has some kind of LCD attached to a few pins. Now, the user program would like to print some text on that LCD, and for that, the developer implemented a few functions called writeByte and writeString. The writeString function takes the string as an argument, and as long as a null terminator has not been encountered, sends each letter one by one to writeByte. In writeByte, we see that this function drives the pins of the Atmega. Some pins of port D are manipulated, then it seems there's a clock signal, and again port D is accessed, followed by a clock signal. The pins are driven manually to get the desired functionality. This becomes dramatically more complex if every single program that requires access to the port D has to come along with the same functionality. Imagine that port D is changed to port B. That means all programs need to be adjusted and recompiled. It would be much easier if there was one program that always runs on the system and the user just sends the string to that program, and it takes care of the rest by manipulating the correct pins to drive the LCD. Like this. We are so used to the printf statement that we don't think about the underlying complexity of that command. For instance, hello world is supposed to be printed, but which process is the terminal process, and how to manipulate the memory of your graphics adapter to see the string emerging on the screen. That is taken care of by the libraries and, in the end, the kernel. In the user program, just the hello world is mentioned to be printed. Let's see what happens. Somewhere in one of the libraries, the implementation of printf exists. This is just a simplified example. In real, printf is a lot more complex. This printf function invokes another function in maybe some other library called vf-printf. And in vf-printf, we will find assembly code. Some values from the stack, represented by the ESP register, are copied to the registers ECX and EBX. And the constant 3f in hexadecimal format is copied to EAX, which is followed by a software interrupt 80, also in hexadecimal. This is a system call, hence the kernel will take it from here. The kernel catches this interrupt and then performs the desired tasks, which includes copying the string from the program's memory to the memory of the terminal program, which then causes an update of the video memory, given that all players, such as the window manager, etc. in between do not object, and for instance the terminal program is covered by some other window. It is not the point of this chapter to understand the flow of data through the kernel, which by itself is an interesting lecture for some other time. What is the takeaway here is the abstraction. Instead of manipulating the pins and writing to memory manually, I have a program that takes care of it, and more, such as security, etc. Can we upload that useful kernel to the AVR? Let's have a look at the list of supported CPUs. There is the Alpha CPU, but also Intel's Itanium, IBM's PowerPC, and Sun's Spark. Also, the new processor architecture of RISC-V found its way into the kernel next to players such as Xilinx Microplace or ARM, often integrated in smartphones. Going through this list, we unfortunately cannot spot any support for 8-bit AVR architectures. The resources required to run the Linux kernel are quite high when compared to the available resources in the avr-gcc CPUs. Therefore, it is better to pick the cherries and to implement only that stuff that we need, and that too highly optimize it in terms of performance. What cherries shall we pick? One of the cherries is definitely the scheduler. Imagine that you can divide the program into tasks such as measuring the temperature, do some computation, and finishing off by communicating the results. Usually developers would write the program like a to-do list, as in first this, then this, third that, and last this functionality. Repeat from the beginning. However, there might be a chance that in some of the tasks the CPU is just idling, spending precious computation time and therefore energy. Especially in battery-powered devices, developers look into how to arrange the tasks so that they interleave. For instance, is there a delay? Okay, do some computations during that delay instead. This interleaving is a very tedious and error-prone work. Programs implemented in such a way are very hard to debug. Therefore, it sounds like a useful cherry to me if there is a scheduler that gives the CPU resources to a different task while one task is required to wait. Therefore, instead of having a list, we have tasks and define dependencies among those tasks. And then we let the scheduler decide when to execute what. Before going enthusiastically into schedulers, we have to talk about a few terms and how schedulers actually work. Imagine we have a system with two tasks. Please note that often tasks are referred to as threads, but also processes or even programs. They are interchangeable, especially in the domain of small MCUs such as the avr-gcc. The system has also two resources which are required by the tasks. Both tasks are ready and the resources are free. Now task 1 requests access to the resource number 1 and task 2 to resource 2 respectively. Since both resources are free, the tasks can reserve the resources for themselves, use them, and continue to run. After a while, task 1 does not require its resource any longer and releases it. Now, resource 1 is free again, while task 2 needs a little bit longer. However, after some time, the system returns to its initial state in this example. Let's restart this example, but this time with a small twist. Again, both of the tasks request for the same resources. And since both resources are free, both tasks get to reserve them. So far so good, and nothing exciting happened. However, to continue to run, task 1 needs to have access to resource 2 as well. However, resource 2 is already reserved by task 2. Therefore, task 1 goes into a waiting state till resource 2 becomes available. Once task 2 completes and relinquishes its control, task 1 returns from the waiting state and can continue. However, the world never works in the way that we want. We land up in this scenario, and now task 2 needs to get hold of resource 1, which is still reserved by the waiting task 1. That is a classical deadlock situation. There are a few solutions available to resolve this situation, and none of them is really pleasant. To solve the issue, one of the tasks needs to be terminated to free up resources. That terminated task needs to restart from the beginning. However, that assumes that the tasks can be terminated. For instance, the killed task could have altered the state of some data in the non-volatile memory, and it is half done. What shall happen with that half? Expensive rollback mechanisms are the result. Apart from that, it is very hard to detect deadlocks, especially in distributed systems. Therefore, the other solution is to avoid deadlocks to occur in the first place. That could be done easily if both tasks had told the scheduler that they eventually need both resources. In that case, the scheduler would have assigned both resources to one of the tasks while the other one remained in a waiting state. The disadvantage is that the tasks do not always need both resources, as we have seen in the very first example, but the scheduler has to assume the worst case every time. That is why, apart from assigning resources to tasks, the scheduler has to make sure that either deadlocks are detected and it needs to have the power to resolve those, or that there are no deadlocks in the system at all, even if it reduces utilization. What else do we need to consider for schedulers? Let's have a look at the scheduler which manages the CPU resource. Fundamentally, there are two distinct scheduling policies, preemptive and cooperative. In a diagram, the preemptive policy is shown. Preemptive means that the CPU resource, that is, its computation capability, is assigned to tasks in fixed time slots. After the allotted time period is over, the current task is rescheduled independent if it completed or not. It will get the CPU again as long as the kicked task remains in a ready state. This happens to task A, for instance here. The CPU is then allotted to task B. However, B was just a small task and did not require the entire time frame as indicated by the black bar at its end. It finished early. After terminating, it informs the scheduler, which also requires CPU resources to determine which of the ready tasks in the queue is next. The scheduler then selects the next task and schedules it for the remaining time left in the frame. As you can see, the time frame is not reset. Its duration remains constant throughout this example. Therefore, task C might not just get enough time here and is rescheduled like task A earlier. In the third time frame, it is task A's turn again. However, unluckily for task A, an interrupt occurs, which has a higher priority and is therefore served first. After that, task A continues. These context switches do not come for free. For instance, after an interruption, task A will continue as if nothing happens. That means task A expects the CPU registers to be in the same state just before it was kicked out. Therefore, every context switch involves that the CPU registers are preserved on a stack, for instance, and recovered from there before the CPU resources are given back to the task. Hence, if the time frames are too short, most CPU resources are spent on context switching overhead. If the time frames are too long, tasks might starve since they wait for too long. Managing all this is the responsibility of the scheduler. Obviously, optimizations can be applied. For instance, if a task does not need all registers, those unused registers do not need to be saved. It is different when compared to the cooperative scheduling policy shown below. This time, the tasks which hold the CPU resource get as much time as they want to complete. The scheduler does not interrupt the tasks with one exception, and that is if the tasks are disturbed by a high priority task such as an interrupt. Now it is the responsibility of the tasks to tell the scheduler that it may consider another task to be scheduled now. Imagine that one task is waiting for some resource. Instead of polling the state of the resource, it could say, maybe later again, and give control to someone else. That scheduling will work if the tasks play fair and nice, and no tasks is hogging the CPU either due to malicious intent, by forgetting to release the CPU resource, or since it crashed. In this case, the watchdog timer could be of help by causing an interrupt, allowing a scheduler to check the health of the current task. And I would like to take the opportunity to clarify a misconception I often encountered during lectures. It is regarding a real-time operating system, or RTOS in short. The misunderstanding here is that the scheduler in RTOS ensures that a task is always completed in real time. That means that there is no delay between a triggering event and the output. However, that is incorrect. The goal of a scheduler of an RTOS is to reduce the jitter of task execution timings. For instance, on the left is the duration of a task execution under normal circumstances. Most of the times, the task completes in around 7,200 cycles, given that the task is independent of any inputs. But it can also take around 6,000 if we are lucky, or even more than 8,000 cycles in worst case. On either side, there is no limit. On the contrary, the scheduler of an RTOS guarantees the execution of a task within a specific time frame. On the right, you can observe this effect. In most cases, the same task spends around 7,230 cycles. There are a few outliers, but we can say that the task completes in 7,230 plus minus 30 cycles, and the scheduler guarantees that. Okay, so far we considered one cherry that we need from the kernel, the scheduler. The other important abstraction for embedded systems is inter-process communication and resource reservation. How tasks can reserve resources and communicate with each other. What can happen if we do not pay attention to that? First, let's have a look at semaphores and mutexes. We also have a look at channels, which allow one task to send data to other tasks. And in that context, we introduce the term atomic access. Okay, consider a system that has two tasks and one resource. This resource has a memory space called A to hold one character. Both tasks are currently in a waiting state as they would like to send a character to that resource. Therefore, by chance at the same time, both tasks ask the resource if the memory space is currently occupied. The resource checks it and replies with a no to both. It does not know why the tasks are asking. Maybe one of the tasks is waiting for a specific value. However, in this scenario, both tasks would like to store different values into that memory location. Now, the resource has an issue. It has to store the value of A as well as B into that single memory location. However, that memory can hold only one value. How to solve that issue? Well, for one, the resource could have lied to one of the tasks when asked if the buffer was full. However, that would mean that the resource knew beforehand that both want to store a value which it did not. A second alternative would be to delay or even withhold the reply for the buffer state request to one of the tasks to wait and see what the other task is going to do. That would reduce utilization if the access is not conflicting, which is the case if one task asks for the state, while the other one asks for the state as well as writes to the memory location based on the result of that state. There are other options, such as increasing the buffer size of the resource. However, that postpones the problem to a later state. None of the options is really satisfactory, and that is where semaphores can play their strengths. Consider the same scenario as before. However, this time, the tasks have to have a lock of the resource to access it. Hence, both tasks ask for the lock first. However, there is only one lock available. Consider it to be like a token. Only if you have that token, you are allowed to talk to the resource. Since there's only one token, it can be given away only once. The loser of that arbitration cannot access the resource. Now task 1 can access the resource undisturbed and without interference from any other player. Again, it asks for the state of the buffer, which is currently empty, then stores the value A, and releases the lock, that is, it returns the token. Now, task 2, which was waiting all the time, tries to get a lock. Since nobody has the token at the moment, task 2 gets it. Then task 2 asks if the resource is full, which it is. Since task 2 wants to write B to the buffer, it cannot proceed at the moment and therefore releases the resource and waits for some time till it retries. As we could see in this scenario, any task that has an intention of modifying the state of the resource needs to have the token. To accomplish that, we have to make sure that we give the token away only once, even if more than one party asks for it at exactly the same time. Therefore, the check for the availability of the token and its handing out, despite being two operations, is inseparable and therefore atomic. If the resource has only one token to give away, as it is the case in this scenario, the token is called a mutex. If the resource has multiple tokens and could allow, for instance, both tasks to write to the buffer because it has the space for two write accesses, these tokens are called a semaphore. Mutexes and semaphores are fundamental when accessing a buffer that allows two tasks to communicate. Usually, one task is a producer, filling the buffer, which acts as a FIFO, that is first in, first out, while another task consumes the stored values. Production and consumption are both write accesses to a common resource, and hence the accessing tasks require a lock before writing to or deleting from the buffer. This mechanism is also called a queue or channel and allows to shift around data from one task to the other. Okay, after talking about the theory of schedulers and atomic accesses, are there any implementations that already exist so that we do not have to reinvent them? It turns out there are quite a lot, as a quick search reveals. By no means this list is complete. Let's talk about some of them. The links to all those schedulers are in the resources folder in case you would like to have a look at them more closely. First, there is the Arduino scheduler written by Mr. Patel and made available on GitHub. The scheduler employs a cooperative scheduling policy, has built-in support for semaphores, and queues and targets the Arduino platform. It only allows tasks which are never ending. That means one-shot tasks that are launched once and then never again are not supported. A context switch is completed in 176 cycles, since all registers need to be saved. We will examine this scheduler in a practical session later in this chapter. How is the scheduler used in the program? First, this Arduino program executes the setup function as usual. In this setup, the scheduler starts another task with two parameters. The first one is the setup function of that task, here setup1. And the second parameter is the loop function of that task. If you're familiar with programs utilizing the Arduino library, you can imagine that multiple setup and loop functions are executed in parallel. As you can see, loop 1 calls the function blink, which turns on the pin, waits for some time, turns it off, and again waits for some time. The same function is called in the normal loop. Therefore, blink is executed twice, one time by loop 1 and once by loop. Where is the part that we said is required for the task to tell the scheduler to consider other tasks? It is hidden in the delay call, which contains a call to the function yield. By including scheduler.h, the yield function has additional functionality, as we will see in the second half of this chapter. First, let's have a brief look at other schedulers. The next one in the list is FreeRTOS. It brings support for some Atmegas, but no Arduino. The Atmega 328P is currently supported through the Atmel Studio IDE, while the other Atmegas through WinAVR, the AVR compiler for Windows. Although porting to other toolchains should not pose a big problem. The big advantage of FreeRTOS is that many CPUs and MCUs are already supported. Hence, if a software developer is familiar with FreeRTOS, it will be quite simple to use it for projects that have the Atmega MCU. Another interesting project is FemtoOS. It supports up to 16 tasks since the maximum is implemented statically in the FemtoOS source. The most interesting part is that sleep modes are supported, but the user has to implement them. In addition, many AVR MCUs are already supported. It seems that the project does not have much track and development, although the forum is still active and the developer responsive. Before considering FemtoOS for your project, it seems that another license is required for commercial projects. How does FemtoOS look like in a source code? Actually, quite simple. The tasks which are supposed to be executed by the FemtoOS scheduler need to start with the string app loop and an underscore. In it, they can be rescheduled at specific times. Here 100, 233 and 123 milliseconds. If the function's name does not begin with app loop, it is not started. If some resources need to be set up, the function has to start with app boot shown here. The Arduino IDE brings their own scheduler called Task Scheduler. It is preemptive and utilizes the 1 millisecond tick counter from timer 0 that also the delay function depends on. Therefore, timer 0 cannot be used and reconfigured in the Arduino sketches any longer. Like in the Arduino scheduler, the very first scheduler that I introduced here, the time requirement for switching context is around the same. It takes about 1 microsecond longer. As usual, as everything in Arduino sketches, the focus is on accessibility and ease of implementation. Tasks and functions are defined and then added to the scheduler. The first parameter of tasks add is the function, followed by the time interval in millisecond in which the task is executed again, and a third parameter defining a delay before the first execution. If the second parameter is set to 0, the task will execute only once. In the original implementation, at maximum 8 tasks are supported, but this can be modified in tasks.h. There is no end to this chapter in discussing the advantages and disadvantages of schedulers available for the AVR architecture. Hence, let's see what the requirements are and the questions to be answered. First, the MCU is to be supported without spending too much effort in porting a scheduler to a new architecture. In addition, we have to consider our current toolchain setup. Currently, in the VirtualBox image, the avr-gcc for Linux is used to compile user programs and not WinAVR. In addition, how easy it is to extend the functionality of the scheduler, and is the developer still around if help is required. Also, is a preemptive or cooperate policy or something in between or entirely different better for the project to be realized? Have a look at the quiz after the session, showing one advantage of a specific policy. Also, for reasons of reduction in power consumption, size, and overall costs, the user program is to be optimized for low power and high performance. Hence, the Arduino IDE is not used, but only AVR libraries. Therefore, function calls to, for instance, digital write, digital read, pin mode, and delay are not available. It will be tedious work to adapt one of the schedulers designed for the Arduino IDE to run without this library. And apart from a small memory footprint in SRAM, as well as flash, it would be an advantage if the scheduler could set the Atmega to sleep if there are no tasks ready at the moment. Unfortunately, not many schedulers consider battery-powered devices. However, there is one scheduler that comes close to those requirements. The next session of this course will dive into this scheduler and practically modify it to fulfill our needs. Considering a simple implementation, what do we expect from the scheduler? First, if the MCU is idle and no task is ready to be executed, the MCU shall sleep to reduce the power consumption. In addition, maybe for a project or maybe later, extensions should be possible and the scheduler has to be independent of the Arduino library and only has access to the AVR library. For the reasons explained in the previous quiz, we prefer a cooperative scheduling policy. The software developer has to make sure that the tasks behave nicely and play a fair game. Preferably, semaphores and queues are already built in. All those wishes make the scheduler already complex. For instance, the AVR library supplies a function to introduce delays, and we used them many times in previous exercises. Recall how delay MS is implemented. Based on the preprocessor macro f_CPU, the library computes how many times a loop has to iterate to get the desired waiting time. During that waiting time, the CPU does not do nothing. It computes the loop conditions, executes some non-operations or NOPs, and the program counter keeps jumping in a loop till the time has passed. How do we interrupt such a process and reschedule it? In the delay MS function, there is no notion of stopping a task and preserving its context. And even interrupts will not work, as the task will continue as soon as the ISR finishes. If the scheduler should also support preemptive scheduling, we have to think about how to handle protocols which rely on software implementations. And so far, we have not even discussed tasks with different priorities. Let's have a look at an example, what a scheduler implementation could look like. We have 3 tasks, task A till task C. Task A and B rely on the delay MS function, while task C waits for the ADC conversion to complete. All those are conditions in which a task could yield and allow other ready tasks to be executed. Let's assume task B is scheduled first. Since the delay is a fixed implementation in the AVR library, the CPU will be busy in that delay loop. After that, we could include a command in the task which yields it and let the scheduler decide to allot the CPU to task A, which is ready. At some point in time, task A will execute a waiting delay of 500 milliseconds. Around halfway into that delay, the ADC becomes ready, and task C is waiting to get access to the CPU while task A is still in a delay loop. After the 500 millisecond delay, task A yields and returns the CPU resource to the scheduler, which decides to schedule task C first, followed by task B. While from the point of view of the allotted clock cycles to task B, only a bit of time has passed, it is different for an observer. The delay between the first 10 millisecond execution and the next 10 millisecond execution in B is more than 500 milliseconds apart. That might break a communication protocol. Here, the problem is that the scheduler follows a strict cooperative policy and the tasks would like to cooperate. However, function calls will not let them. Obviously, a software developer can dive into the source code of the AVR library and adapt the delay function to the new needs. That makes the source code dependent of the scheduler. Let's see if preemptive scheduling is much better. At least it has the option to interrupt the delay MS functions. The entire time that we observe is divided into 7 equally long time frames. After every time frame, the scheduler checks what tasks are ready, and if there are multiple ones, chooses the one which had access to the CPU the longest time ago. Let's see what happens. Again, task B is scheduled first. It relinquishes control after the first 10 milliseconds of delay, like earlier. Since no other task is ready, task A is scheduled. It starts executing the delay of 500 milliseconds. After some time, the scheduler kicks in and checks again the queue of the ready tasks. Now, task B would like to execute the second delay of 10 milliseconds, while task A has remaining delay time left. Therefore, B is scheduled first, since A just had access. At the beginning of the third time frame, no other task apart from A is ready. Hence, the CPU is given back to A. In one point in time, the ADC becomes ready, and after a short waiting time, here marked in dark blue, task C is served. Compared to the cooperative scheduling, this scenario looks much better, since tasks B and C are served much earlier. However, while from the point of view of task A, 500 milliseconds have passed, an observer sees that the task started at 10 milliseconds and lasted a lot longer than 510 milliseconds, roundabout here, in the real world. No matter what policy is employed, there might be situations in which the program does not work. Those situations might never occur or occur in random intervals. Those are the bugs which are the hardest to debug, as the developer has to wait for them to happen and then backtrace. In this scenario and the previous one, the issue was that we cannot interrupt the delay function. Ideally, instead of calling the delay, it could be better to inform the scheduler about the waiting time and let the scheduler come back once the time passed. For example, here, the task tells the scheduler, hey, I have to idle for 500 milliseconds. Please let me know when that time passed. Or here, task C tells the scheduler, hey, I'm waiting for the ADC to finish. Just continue with me once it is my turn. The scheduler could register those requests and make them part of its decision logic. And even better, the scheduler knows what task is waiting for what and can let the MCU sleep to reduce the power consumption. That would be ideal, wouldn't it? Unfortunately, it's not that easy, since not all conditions for tasks are wake-up conditions while the MCU sleeps. In addition, how will the scheduler know how much time is 500 milliseconds or 10 milliseconds? When the MCU sleeps, the time stands still as the CPU is not clocked anymore. While this is the ideal scenario, can we have a working scenario without much complexity and implementation efforts? So what if we again divide our time window that we currently observe into multiple frames? But now the MCU wakes up at the beginning of every time frame and checks if any condition of the tasks to continue has been fulfilled. If there's none, it sends the MCU back to sleep. If there are, it executes the tasks and goes back to sleep when there is none left anymore. For instance, here, task A tells the scheduler that it will be ready again in 500 milliseconds. The scheduler registers this request and makes sure that task A is not ready till the time has passed. In the meantime, it can execute all other tasks and accepts their conditions to continue. The disadvantage is that the desired delay does not end at the beginning of the time frame. For instance, at this time index, it is too early for A to continue, while at this time index it is already too late and A had to wait for that long. Additionally, the same is true for task C. The ADC became ready here, but task C was scheduled only here at this time index. A simple solution to that problem is to make the time frames either longer or shorter, depending on the strictness of the requirements. For instance, a time frame duration of 1 millisecond will make sure that all tasks can choose any arbitrary delays. A longer time frame does not provide that luxury, but since the scheduler does not have to wake up and check for ready tasks that often, the MCU can sleep longer, which is rewarded with a low overall power consumption. Therefore, the software developer has to compromise. Okay, with our wish list, we know what we want. Does it exist? While some scheduler introduced in the previous session covers some features, some others are missing. But one scheduler sticks out, and that is the Arduino scheduler. It does not run out of the box without access to the Arduino library, but after studying the source code, the dependencies to that library are minimal. It does not issue any sleep command either to reduce the power, so some thoughts are required how this feature can be added. And it depends on delay, which is the largest drawback. Probably we have to define our very own delay functionality. On the brighter side, semaphores and channels are already included, and the scheduler employs cooperative policies which provide more control over the tasks. Let's have a look at the scheduler and its implementation. The example that I go through is in the shown directory in the VirtualBox image, or as usual, it is also attached. For this practical session, we will go to Course, Bonus and Scheduler, and there are already a few directories available. That is the source code of the Arduino scheduler Then we have FemtoOS here and free RTOS. I just copied it from their websites for your reference into this directory. This directory contains the solution for the exercises at the end of the chapter. So we are not going to have a look at them now. And this is the working directory for our current practical session. And if I check the content, as you can see, nothing is inside. For the practical session, I'm going to use the Arduino scheduler. However, the Arduino scheduler depends on the Arduino library. Therefore, it is most likely that some source code modifications are necessary to remove those dependencies. However, I would like to keep an original copy of the source code, and that's why my plan is to copy the source for this Arduino scheduler into the exercise directory. And to do so, first we have a look what is inside. We see here some documentation, and here's a README. Here are some examples which I'm not interested in, but the source directory seems to be of interest, and it seems I found the source code of the Arduino scheduler. Therefore, it will be sufficient if I just copy these two files, including this directory, which contains the source code for the channels, queues, and semaphores. Therefore, we only copy the source directory into the exercise directory that we use for this session. Let me rename it so that we know what is inside. Scheduler. Okay, we see usually we use just the file name .c because we are compiling C code. Here we see CPP. That is an indication that scheduler is based on C++, and therefore we cannot use avr-gcc as usual, but we have to use avr-g++ to compile scheduler.cpp. In addition, there's no makefile, therefore we have to create one. And to make life easy, I would like to use the scheduler in the end as a library. And we already used, for instance, UART as a library, and therefore I'm going to recycle the makefile from the UART library that we used earlier. And for instance, we use them in course, memory, flash, and I think there was a last address in flash that we then printed out on the QtCom, so there must be some UART, and here it is, UART, and there must be a makefile that I just copy. Makefile is there. Obviously I have to modify it. Here is C++ instead of GCC, and the library should be called libscheduler. It depends only on scheduler.o, and to achieve scheduler.o I have scheduler.cpp and scheduler.h. that creates then the object file, and then the object file is taken and put into the libscheduler.a. Perfect. Let's save and exit and just give it a shot. Maybe it works. At least we will get some error messages and know what to do next. Okay, there is a preprocessor error which prints out this text. It is located in scheduler.h in line 150, and it says here that this Arduino board is not supported. Why is this error message coming? Let's see what we need and what we are missing. And for that, I open scheduler.h in line 150. And here we are. This creates the error message. And we see here some if-defs, such as Arduino, Arc, STM, and so on. So these are different architectures. And they're all else if, else if, else if. Here's a teensy Arduino. And it seems that we have to select the architecture that we are using. This looks most promising. We have to define this macro to activate the default stack size of 128 and to prevent that this error message is printed because some elif branch has been analyzed and not this one. To keep the source code changes minimal, obviously I can go up and define it here somewhere in the same way that we are used to, like this. But I would like to keep the source code changes at the minimum, and therefore I use another method to define Arduino arg-avr, and that is in the make file. We already used it to define the speed of the CPU. This is -d, then the name of the macro and its value. That is equivalent to define f CPU and then this number in the C source to be compiled. The effect of this parameter is the same as this one. Okay, that means I can just add it and then the name of Arduino arg-avr. There we go. Save it and recompile. Okay, in scheduler.cpp in line 20 is an include of Arduino.h. I don't want to have the access to this library, and that's why let's remove it and let's see how far I can go. Scheduler.cpp line 20, remove it, save it, recompile. Oh, there are just a few messages. RAM-end is not declared in the scope, so we have to find where RAM-end is. And memset, which is a standard function in the string library. Okay, let me go back to the header file that we had earlier. The make file I don't need any longer. So what we do is we include the string .h for memset, and RAM-end. Where do we get RAM-end from? It must be part of Arduino or the AVR library. Let's search for it. The library is installed in opt Arduino, and I'm going to search all the files recursively through all directories for the definition of RAM-end, and everywhere, all the files. Let's see what's happening. Okay, it seems RAM-end depends on the MCU that we are using. This directory contains all the header files defining, for instance, the addresses of the port and so on, and this is the header file that we always included, which then includes one of these depending on the selected MCU. So there must be an MCU called IOM C28P, and here it is. It should contain RAM-end, and RAM-end is 8FF in hexadecimal format. It's the last on-chip SRAM location. We have 2 kilobyte of SRAM, and this is the very last address. Okay, so RAM-end we simply get by including io.h. So as usual, include io.h for RAM-end, so that we remember later in case we have to debug something. Let's save it and let's try. Oh, my mistake. It's not io.h, but it's avr-io.h. Now let's try. Alright, that was fairly easy, to be honest. It compiled without any errors, and we have our libscheduler.a now. Let's write our blinking program that utilizes the libscheduler now. As you can see, nothing is here yet. And again, I'm recycling one of the earliest exercise that we ever had, and that was in course blink avr. There's a blink.c, and I also take the make file. First I clean up everything, and then I move blink C to blink C scheduler, so that we know. Obviously you have to change it in the make file as well. Scheduler. Let's modify our scheduler. And we don't need these comments any longer. We know exactly what's happening here. Okay, how do we invoke the scheduler now? And for that, let's have a look at the website of the scheduler. I already opened it, but I also placed a link here. So you can simply click on this and it goes to the GitHub website of the scheduler. And scrolling down a little bit, it says here, the scheduler is started with task setup, that is the function that is invoked once, and a task loop, that is the function that the scheduler loops through, and optionally a task stack size. Okay, let's do that. That means I have to put this functionality into a function call. Let's do that, and let's call it void blink 0 loop. No parameters. Nicely aligned. And I want to blink port B4, and that too for 250 milliseconds. Then I have a void blink 0 setup, in which port B4 is changed. And now the documentation says scheduler start first the blink 0 setup, and then the blink 0 loop call. The thing is, the functionality that I would like to have in the end are 3 different LEDs blinking independent of each other. And I would like to avoid to clutter my source code with a lot of tiny little functions. Therefore, instead of implementing 3 different setup functions, I just define DDRB to be an output right here, and that too only once. And then I can skip implementing this. Or DDB3 or DDB2. Fortunately, the documentation says if there's no task setup, then there's another function call that we can use, and the task setup is just missing here. It's the same as this one, just without a task setup. And that's what I'm going to use. It's called loop. Okay, so I don't need this one, but I need 2 more of these. blink 1, blink 2, port B3, port B2, and also the timings should be different. So let's say it is 300 and that is 750. So my understanding right now is that the scheduler will get a task, that is the blink loop, and will execute it as long as there is no other task to be scheduled. Now both will blink, blink 0 and blink 1. That means the task is taken and added to the scheduler. This task is taken and added to the scheduler. And now I have my main task, in which I just call blink 2 loop. What I also could do is write it like this. But since the scheduler considers the main as a separate task, I can implement it like this as well. Obviously, I have to include the scheduler. Scheduler.h and save it. Now let's modify the makefile to include the scheduler as well. Includes here Arduino scheduler, that is to find the header file, and the library is here as well. Yeah. And we have to use L scheduler. Then we have to add it to the compiler so that it knows to use the library of the scheduler to compile our executable. Let's see. Alright, first mistake, we still use GCC and not GPP. Means we have to change it here to make the class of the scheduler available. Okay, we have the same error message that we had earlier when we compiled the Arduino scheduler. Means I have to add Arduino hard avr, if I'm not mistaken. Let's build it. And it compiled. We have our executable ELF and our hex file. So let's upload it and let's see what happens. So I have my 3 LEDs here, and let's upload the program. Oh, the port for this particular Arduino is ACM and not USB. So let me change that real quick. Okay, the yellow one is blinking, but nothing else. Did we make a mistake? Currently, it's the understanding that the scheduler takes this task and schedules it. Then it takes this task and schedules it together with this task. So what happens if I add the blink 2 into the scheduler as well? Like in this way. Let's try. Nothing happens. It seems that the start loop call is ignored. Earlier we had blink 2 working, that was here outside of the scheduler, but now it's part of it and nothing works. And to understand what's happening, we have to have a look at the source code of this scheduler. So let me put this to the side. Bonus scheduler exercise, Arduino scheduler. So what happens actually when we call start loop? Let's see the definition of start loop in the header. I have it open somewhere else already, probably from the earlier changes. Start loop. Start loop takes task loop as a function, and the stack size is optional. And then it calls start with null, start loop and the stack size, and start is right here. That is the setup that we don't have, that's why this is null, and the task loop and the stack size. So we have to find what the implementation of start is. And that is defined in scheduler.cpp. This also open somewhere. Let's search for start. Alright, it starts with some checks, if it's null and so on and so forth. Then it allocates the stack size. Then initializes the stack and so on and so forth. And in the end, just before returning, it initiates task with given functions and stack top. So init seems to be interesting. Let's see what this does. So the queue containing our tasks seems to be a double linked list. So our new task is added here. And then the context for the new task is created, the caller will return. And then we have a set jump here. And as parameter, it takes the task context. What does set jump actually do? And to understand set jump, we have to check the internet. Let's go to the cppreference.com. It saves the current execution context into a variable enf. So this variable enf in our case is the task.context. This variable can later be used to restore the current execution context by long jump. So it seems that set jump and long jump come in pairs. That is, when a call to long jump is made, the execution continues at the particular call site that constructed the context variable passed to long jump. In that case, set jump returns the value passed to long jump. The other option is that set jump is called without long jump. And if we scroll down a little bit, it says here that the return value is 0 if the macro, that is set jump, was called by the original code and the execution context was saved to env. Since that is the case for us when we call set jump in the scheduler code, it means that set jump returns 0, and since the set jump is the condition for an if, this if condition is false in our case. If that sounds too weird, there are other explanations what it does. For instance, here in tutorials point, here's it again, set jump, the macro saves the current environment, that is the context, into the variable environment, that is our task.context, for later use by the function long jump. Okay? If this macro returns directly from the macro invocation, that means if I just call set jump and that is it, it returns 0. But if it returns from long jump, then a non-zero value is returned. So if I have a look at the init now, I haven't passed any long jump so far. The only long jump that is here is in yield. And yield, it's not executed so far. Right? So I came from start loop, I went to start, then I did the stack allotment and allocation, and then I went to init. I did not go through long jump. That means after saving the context, this set jump returns 0. This is false. That means these two lines are not executed at all, and the init function returns. And that is why nothing blinks. So the scheduler takes the task and adds it to the task queue after allotting the stack to save the context, and then it jumps back, and then blink 1 is added, and it's again added to the queue after allotting the start context, and the same with blink 2, the third function call here. And that's why nothing happens. And when I had this implementation, the port B2 was blinking, indicated by the yellow LED, while this was ignored because this returned with 0. That means I have to make sure that long jump is executed somewhere, and for that I have to invoke yield. So let's do that. After blinking, the task can yield, or more precisely, I put it here. Okay, let's see if it works as expected. Okay, we see something blinking. However, the pattern looks a little bit odd. The yellow LED, that is this one, should blink in an interval of 750 milliseconds, while the middle one, the green one, with 300, and the red one with 250. However, it looks like as if there's a pattern, and they always blink in the same sequence. So what is happening here? Blink 0 is added to the task list of the scheduler, but it's not executed because this returns 0. Then the same happens with blink 1, so it's added to the task list, and this is not added. However, the scheduler considers the main while loop also as a task which is automatically added when scheduler hedge is included. Okay, let's say the scheduler starts with this one. It goes into the function, toggles the yellow LED, waits for 250 milliseconds, and then tells the scheduler that this task is yielding. That means the scheduler checks what other tasks are in the list and chooses one of them, either this one or this one. Let's say it chooses this one. Hence, the green LED is toggled, it waits for 300 milliseconds, and again, the task yields. Now, since this task and this task was executed last on the CPU, while this was not executed at all at the moment, this task is selected, the red LED toggles, it's waited for 250 milliseconds, and the task yields again. And then it continues, since the scheduler chooses then this task, again because this was in waiting state the longest time from all three. And it continues. Therefore, you can see that these delays are always the same. They are always executed to the fullest extent before the task is yielding. So you might think that a solution to that would be to yield before the delay. But once the scheduler switches back to this task, this delay is going to be executed. So there won't be any difference. What I have to do is I have to yield inside this delay, in fact. So one solution could be to split this delay. For all three. That would ease the problem, but only to some extent. In the end, what I have to do is I have to reduce this delay to the minimum, that is 1, and yield, and write this 750 times at least. That means I'm going to have a loop here that starts from 0 to some value that I don't know yet, and then I execute these two lines several times. The question is now, what is this value, this upper bound of the for loop? This will definitely take 1 millisecond. However, we do not know how long this will take till the scheduler reschedules us. So the yield function call will take some time, as we have seen in the presentation, and these blinking loops will also take some time. Therefore, it is very hard to know the upper bound of this for loop. It will be definitely less than 750, but how much? We don't know. How does this work in the Arduino IDE? Originally, this scheduler was targeting the Arduino IDE. The software developers of the Arduino IDE don't use delay ms, but they use delay. That is definitely one difference. Are there any other differences? Let's have a look at one of the examples that comes with the scheduler. So there's also blink, that is good for us. Let's have a look at it. We have here the setup, and we already know scheduler.start, setup 1 and setup 2 and so on, and loop 1 or 2. Let's see what's in that loop that is more interesting. There's a function called to blink, the LED that's supposed to blink. So here's LED, LED 1 and LED 2 with an integer. And I suspect that this integer is the interval in milliseconds. Let's have a look how blink is implemented. Here it is. Yeah, so the first parameter is the pin, the second parameter is the time in milliseconds. And then there's a digital write, a delay, digital write to pull the pin down again, and a delay again. In the entire source code, there's no yield. So where's the yield now? I suspect that the yield is part of this delay call. And to be sure, we have to check how delay is actually implemented. And for that, we go again to the Arduino library. I suspect that the prototype of delay will be in the Arduino.h, so we have to find this function. Let's search for it. Arduino.h. Let's see where it is. Here it is. Let's have a look at it. And we search for delay. Okay, this prototype is here. It's a void, so I can use this text to search for it. fgrep void delay. Otherwise, the implementations depend heavily on the delay, so I will get lots of output. But if I write void, then only the function prototype and function definitions will be given back. This is my prototype, and here's the implementation. So let's have a look at it. Delay, and here it is. What happens here? The micros are executed, and then as long as this is greater than 0, it's yielding. So here is the function call that makes a task yield, while this while loop waits for 1 millisecond. And micros is here, and we see that it depends on the timer 0 overflow count and timer 0. And that is the reason why Arduino sketches cannot utilize the timer 0. It is used by the delay function. Okay, so it seems we have to implement our very own delay functionality. So let's revert these changes that I did here. And I'll call this function simply delay. And the yield will now be part of the delay. So what I do is I replicate the delay functionality from the Arduino library for this case. And for that, let's create a new file. Let's call it delay.c. I like to note down where we found this information, so we don't have to search for it again. And this was the file. Alright. This is just for later reference. I'm going to have a delay.h for the function definitions. I'm going to have, let's say, a start timer. Don't interrupt in case the timer is in power reduction mode. Wake it up, we need it. In case the power are active. Set timer 0 such that it ticks every 1 millisecond. Now if you refer to the lecture where we discussed CTC mode, you can follow these steps easily. First, we have to define OCR0A, that is the compare match unit. We have to activate the CTC mode, and we have to set the prescaler. The timer lecture will tell you how to get these numbers. According to the datasheet, if WGM01 is set, then CTC is activated, and the prescaler I'm setting to 64. So let's see how we got this number. Okay, 16 million, that is the clock frequency. These are the number of timer ticks or timer increments per second without prescaler, but now I have a prescaler of 64. That means the timer ticks 250,000 times per second. However, I just need 1 millisecond. Therefore, I have to divide it by another 1000, and the timer ticks 250 times for 1 millisecond. That means the OCR0A has to wait till the value is 249 because we are starting counting from 0. So if I start counting from 0 to 249, I have 250 ticks that I have to count. Okay, according to the datasheet, prescaler 64 is active if CS01 and CS00 are set. Commented prescaler 64. Then I have the timer mask. I want to have interrupts. And the compare match unit of the timer should cause an interrupt. Let's reset the timer just to be sure and safe, because it started already counting. And I have to count the number of milliseconds that have passed. That means I'm going to have a global variable which is really long. Let's call it timer count. And in case somebody calls start timer multiple times, I have to reset this to 0. And then I activate global interrupts again. Okay, my ISR is just incrementing the timer count. Okay, so far I just set up the timer. I don't have any delay functionality that we have to somehow implement as well. Therefore, void delay. As soon as a task calls the delay, I have to check what is the difference between the current timer count and the timer count that will be after the delay is over. And for that, I compute the end time when delay should return, that is timer count, plus the desired milliseconds. While the end is larger than the timer count, I yield. But before trying this out, let me refer to the header file of the scheduler once more. Because when I went to the header file, I observed that there is a await define. It is basically syntactic sugar, which makes it easier to write programs. Instead of while with a condition and yield, you can also use await. That means we can wait for a particular condition to arrive. In the lecture we had task C waiting for the ADC to complete, and this is a condition that a task can wait for. And in our case, we await the event that end becomes smaller than timer count. And that's it. Here I forgot the scheduler. It means yield and check if there are other tasks. And then we don't need this while any longer. Alright, let's create a header file for our delay C file. A new file. And then I just copy the function definitions. The include guard. so it cannot be included multiple times. And I definitely need to include some avr files, and that is avr-io.h. Then include the interrupts. And since I use await, I also have to include the scheduler. Okay, now the only thing left is the makefile. And it seems that delay is in the wrong directory. I was actually in Arduino scheduler and created these files there. So just let me move them. Sorry about that. Here they are. We have to add them to the objects. To compile the ELF file, it depends on the objects, and that is blinkscheduler.o and delay.o, and this rule determines how to compile the C code into the object code that is required for the ELF. Therefore, delay.o is sufficient to be added here. Let's save it, and I have to adapt our blinking source code. That is, I have to include delay.h to make the delays available here, and I have to start the timer. Start timer. Otherwise, nothing is going to happen. Let's save it and let's try out if it works. And as you can see, the LEDs are blinking now. The fastest should be the red one, with an on and off phase of 250 milliseconds respectively, followed by the green one with 300. And the last one is the yellow one with 750 milliseconds. And as you can see, they are blinking independently. That is the end of the practical session. Let me shortly show you what you have to do in the exercises that is given at the end of the chapter. The task is to take the blink scheduler C code that we just implemented and optimize it for power consumption. Currently, the consumption is at around 57 milliamps, and if the power reduction techniques are employed, then it should look around something like this. Again, you can see that the LEDs are blinking independently and the power consumption reduced from 57 milliamps to around 40-41 milliamps. Please keep in mind that this Arduino board needs around 20 to 30 milliamps as well. In this view, the power consumption has been reduced quite significantly. So think about how to solve this problem. For your reference, in case the exercise was too fast, I'm creating another directory here called solution, and I copy everything that we did into the solution. When you start the VirtualBox image and follow this practical session, you will see again an almost empty directory. And with that, let's head over to the lecture slides again. After modifying the Arduino scheduler and implementing a delay functionality for the scheduler, suddenly the Arduino scheduler became an Arduino and AVR scheduler. Support for the AVR libraries are added, and the delay_ms functionality has been replaced to let tasks yield. If the practical demo was too fast, feel free to rewind and go slowly through the implementations. If there are issues, please let me know in the Q&A box below. What we did not implement is the sleep functionality that is still left. This is part of the exercise at the end of this chapter. Do not think about it as a very complicated problem. The solution to add support for sleep is surprisingly simple. Have a look. So what did we do in this chapter? In the beginning, we talked about the Linux kernel, but swiftly moved over to discuss schedulers in more detail, as this is something that seemed to be more useful for small embedded systems. We discussed preemptive and cooperate scheduling policies, and shortly real-time operating systems, before heading over to the semaphores and channels of inter-process communication. In the end, we took the Arduino scheduler and modified it to serve our needs. Only the sleep mode is missing, which is part of the following exercise. I'm also hoping that your journey was as interesting as mine when I created the lectures, and you made discoveries on the way which have a positive impact on your career. See you in a bit, and thanks for watching.